Welcome to this video, which is supplementary, and will explain how to use the MATLAB code to manage and interrogate the different images that we can obtain from the techniques that we have put in the paper. Supplementary Material 2 shows this figure, and you can see the data flow in between the different blocks and steps of the image analysis pipeline, and the QPAT step in which we produce the semantic segmentation is fundamental to allow microtexturally informed navigation of the sample. Then the user can select a region of interest and hover around into the face map to produce this number of plots, such as the null matrix, histograms, bin scatter plots, screen and contribution plots, and dendrograms. The image representations that you see in block C, they will be registered and they will be input as well into the segmentation. So this is a multi-step process in which segmentation, which is supervised learning, and unsupervised learning are combined, and also the original data is brought to the user for navigation and interaction. If we go to the MATLAB code, the first thing that we are going to see is that the images are located in a directory, which in this case correspond to this directory for the hardbook guide. We need to load the semantic segmentation, the XY maps or stacks, and the image representations that we want to see optionally from the semantic segmentation map. So if we run the first section of the code, all of these will be loaded into the workspace as roots and image files that we can see here. But fundamentally, they are being loaded as quantitative maps or the log base 10 of the quantitative maps. They are used separately. The first group are used for the histograms and the second for the multivariate statistics that we're going to show. Then with retrospective feedback, we are allowed to select which elements do not include into the element list that we are going to analyze. And the bad list for the hardbook eye sample corresponds to these artifact images. So once we load that, the script already knows which minerals he's going to analyze, ranked by abundance, and which elements. In the next step, this is an optional pre-check of the images that we can see the heat maps of calcium or iron, chromium, to be able to know whether to include it or not into this list. And in the next section of the code, we are going to parameterize the ROI tool. So let's leave this by default, and we're going to be asked whether or not we want to select the following four minerals that we pre-selected. If we select orthopyroxene, which is number one, it's going to appear in the histograms as orthopyroxene. And the other minerals are going to be shown with the different elements are in this list as well. And the plots for the bin scatter plots have been selected with iron and chromium. Then once we have parameterized the ROI tool, we can run the interaction step, and we can see here the ROI tool showing us the different plots that can be switched around the sample. So let's say we want to analyze this area of the sample or this area, that will automatically upload the plots. That way we can compare the absolute and relative abundances and multivariate statistic relationship between the variables or elements. This is the model mineralogy. This is the null matrix, which is the abundance of zeros in the data. If the data is sparse, has a very low abundance of positive pixels, then we don't want to include those combinations between minerals and elements into the multivariate statistics. There can be criteria to replace those values so that we can get above this blue line or plane that signifies which elements are going to enter into the statistics. Then the bin scatter plot shows the distribution for these two elements in the different minerals and the number of pixels for each one, and the histograms that are fundamental to compare two specific areas. Then we can do the biplots and script plots with contribution plots to be able to see the variance amount that we are describing. This is three-dimensional. If we want to see the relationship in 2 dimensions, we can use dendrograms. They summarize the different relationship between the elements. The height corresponds to the linkage distance between the eigenvectors of the different elements. In this case, we're including a number of principal components from 1 to 4. So the advantage of seeing stuff in 2 dimensions is that we can include as many components as we want, which will be informed by the contribution plot and the script plot. Thank you for your attention, and I hope that you can use this tool for your chemical maps, not necessarily synchrotron maps, but they can be of any kind, as long as you make the ROI tool big enough to support a higher number of pixels, which makes the statistics more steady. Thank you very much.